Welcome back to Mr. DuPage's classroom. This lesson is for my Algebra 1 class. It is 8.8 Exponential Growth and Decay. This is more about the decay level than the growth. Alright, the first thing we want to talk about is this vampire hunters. So the other day we learned about the vampire epidemic that is going to hit the world, and now we need to find out how we're going to fight back. Let's think back to our opening example of exponential growth and using it to prove vampires couldn't exist. Today we want to extend that idea to exponential decay. So imagine as the vampire epidemic grows, groups of vampire hunters form to combat this threat. Let's say they can eliminate 2% of the vampire population per week. Use the exponential growth function we made for vampires and create a new exponential decay function that represents how many vampires are left after each week to answer the following question. If the vampire hunters started hunting after the 12th night of the vampire epidemic, and assuming no new vampires were made after the hunting started, how many vampires would be left in 8 weeks, 24 weeks, 52 weeks? Alright. So the first thing it told us to do is to use our exponential growth equation from the vampire vampire example that we used the other day. Okay? So what is the exponential growth equation we are using for the vampire epidemic? Well, that was y equals 1 times 3 raised to the x power. What was the starting number of vampires? Well, we had 1 to start with, and we were multiplying by 3 every night. So that is how we got our formula. Now, the numbers from our example were 1 on night 0, 3 on night 1, 9 on night 2, 27 on night 3, 81 on night 4. On the 12th night, what we can do is figure out how many there would be on the 12th night. So y equals 1 times 3 raised to the 12th power, which would get us around about 531,441 vampires on the 12th night, or after the 12th night. Okay? So that is how many vampires would exist using exponential growth. Now we will need to write an exponential decay function to represent the vampires left starting after the 12th night. What percentage are eliminated each? This is not night, this should be week. What decay rate does this represent? What is the start value? Okay, so the first question it asks is, the start value is the last question. What percent are eliminated each week? Well, from above, it told us that 2% are eliminated each week. What decay rate does that represent? I would take 1 minus 2% can also be written as 0.02. So 1 minus 0.02 will give us our decay rate. 1 minus 0.02 would get us, what is that, 0.98. Okay? And what is the starting value? Well, the starting value is the number of vampires after the 12th night. So 531,441. So now what we can do is write a decay function, which would be y equals our starting value, 531,441, times our decay rate, which is this 0.98, raised to, we're not sure how many weeks yet, so it's going to be to the x, okay? Because x is our time. It has not, in this situation, given us exactly what time it wants. So now in question 3, though, it does start giving us times. So for 8 weeks, if we have 8 weeks for our vampire hunters to go out and hunt these vampires, it would be y equals the 531,441 times 0.98 raised to the 8th. If we raise that to the 8th power, we end up with about 452,130 vampires left. About that, okay? So then we look after 24 weeks. It's about 6 months. We'd have y equals 531,441 times 0.98 raised to the 24th. Let's see how many vampires that would be. That would give us about 327,251 vampires. So they are chipping away, but not doing a great job of getting rid of these vampires yet. And then 52 weeks, which is 1 full year. Y equals 531,441 times 0.98 to the 52nd power, which would be about 185,871 vampires. So even after the vampires stop being able to make new vampires after night 12, and we have vampire hunters, it's still going to be 185,871 vampires after an entire year. So as you can see, depending on what your growth rate is or your decay rate, that will determine how fast or how slow we will grow or decrease. All right. Well, all right, let's move on to our worksheet or our actual note sheet. Okay. Remember that exponential growth and decay can be modeled as y equals a times b raised to the x power. The number of students remaining at school after the end of the school day decreases by 80% per hour. Well, let's talk about this 80%. Can be written as 0.8. Okay? If there are 1,600 students enrolled in the school, use an exponential function to model the situation. Approximately how many students are still at school after 4 hours? So let's list the important information and sign labels for x, y, a, and b. X would be the amount of time in hours. So time in hours. Y would be the total population. A would be the initial population, which we can actually know. The initial population in this example was 1,600 students. And B would be our growth rate. Well, since it is decay, I'm going to take 1 minus 0.8, which would give us a growth rate of 0.2 per hour. Okay? So now I can write an equation. It would be y equals our 1,600 times 0.2 raised to the x power. The last thing it asks us is to go ahead and estimate our answer using 4 hours. So it would be y equals 1,600 times 0.2 raised to the 4th power. That would give me about 3 students left after 4 hours, which does make quite a bit of sense. 4 hours after school's over, usually all the basketball or all the sports teams and everybody else are gone from the school. Rarely would I even think there'd be 3 students left, honestly. All right, let's look at the next example. In 1980, the population of Warren, Michigan was about 161,000 people. That's going to be my A value. Since then, the population has decreased by about 1% per year. Well, 1% can be written as 0.01. To find out my B value, it would be 1 minus 0.01 because it is decreasing. So about 0.99 is my B value. So we need to write an equation to model the population of Warren since 1980. So it would be y equals our initial value of 161,000 times my decay rate, which is 0.99, raised to the x power, because we do not know how long it has been. In part B, it tells us to estimate the population in 1990. Well, 1990 is my new population, 1980 was my original. So in that situation, I have 161,000 people times the 0.99 rate raised to the 10th because it's been 10 years. That would leave me with about 145,606 people. The decimal I actually got when I typed this through my calculator was 145,605.5. So because it's population, I'm going to round to the nearest whole number. The 5 would make this 5 a 6. Okay? If this trend continues, predict the population in 2015. Well, we need to know how long it's been from 2015 or from 1980 to 2015. So I'll take 2015 minus 1980, which would give us 35 years. So we're going to raise to the power of 35 in this situation. So y equals 161,000 times 0.99 raised to the 35th, which would give us as an actual decimal 113,255.07, which is about, again, I'm going to round to the nearest whole number, so the 0 will not change my 5, 113,255 people. Well, that is the end of our lesson. The most important thing to realize here is that if I have exponential decay, I am actually going to take 1 and subtract my growth rate from 1 in order to figure out my new growth rate, as I did in that example with part B right here. That would go in place of my B value in my equation, which is in between the parentheses. All right, well, if you have any questions over this lesson, please make sure you come in and see me. Otherwise, thank you very much for watching the video, and have a great day.